Okay, so let's start our lecture today. Thank you for coming. And I know it's very tough, but since I'll be traveling tonight and I'll be away next week, I don't want to skip two lectures. So this is why I wanted to still do it, the recording session. So today we'll be talking about power supplies, which uses the knowledge we learned last week, the power amplifier, as well as the transistor amplifier. So we'll see how it is used. And power supply is commonly used in your chargers in your laptop, your desktop PCs, servers, and etc. It's one of the important modules in electronics because most of the failure actually in these days happen in a power supply or interconnect. So it's very important to understand what's going on there. A power supply is to provide the power to electronics, of course. All electronic circuit requires power to operate, and that's what the power supply does. And if you open up the typical power supply in a PC or in your chargers, especially those switching mode, the core-based ones, then you have an ion core, which is very heavy, and you will see the supply unit inside with a large capacitance. And as I said, the power supply is the prone unit that fails. Most of the time, the transistor itself doesn't fail, but the power supply does, right? So electrical power supply converts the former electrical power to another desired form. And in Singapore, we use 230 volt AC with the 50 hertz. In US, they use 120 volts with the 60 hertz. You convert sometimes wall-mounted supply like we see there. Sometimes you convert the energy harvesters or a solar panel into a different form of energy, let's say DC supplies. Solar panel generate 0.5 to 0.6 volt typically in DC, and you cascade them to have higher voltage in DC. But we need to convert that into AC for AC supply appliances, or vice versa. The PCs, also tablets, they use the DC voltage. Typically, the core voltage is no more than 1.2, but the I/O is 3.3 or 5 volt. Sometimes the PCI Express uses even as high as 12 volts. So then you have to convert, you have to convert that into higher voltage level from the wall-mounted supply into different level. That's what's going to happen in power supplies. This is what the computer power supply looks like, and we still use this type of supply. By the way, recently, when I say recently, 1 month ago, one of my servers, do you remember that we had an E4 which had the power shutdown? The entire building had a power shutdown over the weekend. And during that, after the power came back, the power failed. So my server died, and so I was hacking it. I was taking a careful look at it and found that one of my power supply actually had a bursted capacitor. So electrolyte has bursted out. And that's a small, I'll say, failure. But as I said, the power supply these days is the prone unit that may fail over time. So you need to watch out for any appliances that dies away. It's most likely the power supply or the interconnect that fails. And good news is that I replaced the power supply unit, and then now the server is back on. Now, the electricity generation, in order to understand the power supply, we also have to see what happens from the generator plant all the way to your appliances. What are the delivery of power and electricity happening over these? And in order to understand that, we also need to take a brief look at the history of this AC versus DC. I don't know, have you seen the movie called Current War? That's the competition between Thomas Edison and Nikola Tesla. Nikola Tesla was working a supporter of AC. Thomas Edison was the supporter of DC. Anyways, you know that the AC won, and there's a good reason for it. We're coming to that in the coming slides. But let's take a look at the energy consumption and sources of energy worldwide. First of all, we have the US. You can see that 1/4 is petroleum-based. The other quarter is natural gas. And only the other half is nuclear, electric, or renewable energy. There was some renewable energy boom 10 years ago, But we quickly learned with the recent unfortunate case in the Russia and Ukraine, we had a natural gas, which was supply was diminishing. And that actually kicked back us to look into tap into the more natural gas or even petroleum resources as well. These are really heavily, people are still heavily rely on it. For the renewable energy, there are a variety of hydroelectric, wind, or biofuels, or even wood. Those are the renewable-based energies that people are trying to tap into. But it's not taking up as quick as we might be thinking. And if you look at the source of electricity in France, it's very interesting. France is a unique country in the EU. Over about 3/4 they're relying on the nuclear power plant, and the rest is about hydroelectric and the gas and etc. And you might have heard that Germany has around half of its power generated by renewable energy, right? And the reason it is possible to have half of energy from renewable is because they have their neighbor country called France. They rely on 75% of their electricity on nuclear power. What do I mean by that? So the renewable energy has ups and downs. Sometimes you have more generation, sometimes you have less generation. And if you're short of supply, in France, the Germany, what they do is they tap into the power grid, and the grid is connected to France as well. And since France has more stable power source with the nuclear power plant, they can tap into this. So if every country is relying on 100% renewable energy, then it will be not good, because unless we have the electrical storage to store the energy, then the ups and downs cannot be regulated. Anyway, when you look at the history of electricity generation, that's when the Michael Faraday discovered that the potential difference is generated between two ends of electric conductor. So basically what the generator is the opposite of motor. So motor is if you apply voltage to magnet, and with the static magnet, it will be rotating. And if you do the other way around, by rotating the motor, it will actually generate the electricity out of its two terminals. That's how the Faraday disk is working. It's called a generator. So if you're going to turn this with the hydropower, then it's hydro-powered generators. If it is generated by other means, you can also use the generator to generate alternating current. Now, when the power is generated, I asked the facility to turn on the AC. Anyways, it happened to my previous lecture from 9 to 12. I was surprised because for 8 years of NUS life, I never booked separately AC. I only booked a room and AC was there. And this time around, they're saying I have to book the room. Separately, I have to book the AC. So I don't book the hotel room and then separately AC, right? When I book the room, I take it for granted that the AC will be there. Anyways, the electrical power transmission is used to elevate the voltage and then transmit. Because we'll come back to that, there's a good reason for it because of the efficiency. Now, this is one of the reasons why AC took over the DC. Although the electronics are using DC, the transmission of power and then the appliances still reuse the AC signal is because it's more easier to boost up the voltage there. All right? So the the tower that you're seeing over here is using 500 kilovolt, and that's really, really high. And you might be thinking, this is also relevant to what we have learned from lecture 1 about the capacitance, right? Capacitance 1 over SC, which is 2 pi FC over 1. And this has the capacitance, right? Capacitance is impedance. So if you use actually an insulating glove for the wall-mounted supply here, 230 volt, if you have a good insulating, let's say, good insulating glove, you touch it, probably you are safe. But this, like say, going above, let's say, tens of kilovolts, even with this insulating glove, remember insulating glove means you have a capacitance. Capacitance has a high resistance at low frequency, but it's a finite resistance. So if the voltage goes too high, actually there will be considerable amount of current flowing to your body. So you don't ever even touch 10 kilovolt or higher power line with, even if you have an insulator, perfect insulating glove with the perfect insulating shoes, you don't even attempt that because you will still have considerable amount of current flowing through your body. That's very dangerous. Now, anyways, this transmission of high power will be involving elevating the voltage to a higher level. And that's because of the efficiency. Why? Because the power loss in transmission is strictly relevant to the resistance multiplied by the current square. It means the voltage multiplied by the current. And the voltage is R multiplied by I, which means resistance multiplied by I squared. So it means that if you have a finite resistance in the transmission line, although the resistance of the transmission wire or the line is not that great, it has finite value. So this one is fixed. So in order to lower the power loss as much as possible with the finite existence of resistance, you can see that the current has to be decreased. And how do you decrease the current? Is by, if you just convert it, Ri squared is R multiplied by P divided by V squared, which means R multiplied by power squared divided by the voltage squared. And if you have the finite power that is generated from the power plant, you can easily see that if you increase the voltage, then the loss during the power transmission line will decrease as well. That's why if you have the power plant, when you distribute the power to your local, you always elevate the voltage. And during that process, actually, voltage in AC is much easier to elevate and decrease than that of DC. All right? And distribution, this is what I call the electricity distribution. Typically, this one you don't see in Singapore anymore because we have everything underground. That's where you always see the maintenance people always digging up again and then exposing and doing the maintenance in Singapore Power. But anyways, you have implemented everything in the underground these days. But if you go to the suburbs of the other countries where the land is too vast to have everything underground, then you still see this on outside, which translates the 111K kilovolt into the 400 volt or 230 volt transformers. So 230 volt will be single phase that you see in the wall mount. 400 will be three phase for higher power appliances in factories or even for labs where there's high power equipment. We use three phase 400 volt, even in Singapore. And 400 kilovolt and 300 kilovolt distribution network is underground in Singapore, so you don't have to worry about high voltage. Now, for the wave currents, I have briefly mentioned to you, Thomas Edison was supporter of DC, and he claimed that the AC is dangerous. Whereas Nikola Tesla, because of obvious reason about the power loss, power loss, the less if you increase the voltage, and he knew increasing the voltage in AC is much easier to do so than that of the DC. He was a supporter of AC network. And we know that actually Nikola Tesla won in that he was right in using AC power line. So that's why everywhere in the worldwide we are using AC network these days. And then I mentioned that it's easier to transfer the voltage from one level to the other in the AC. And how does that happen? In AC, we use something as a transformer. And if you look at the graph here, this is the transformer that translates the 11K to 400 or 330 volts. And we'll look into how that transformer works. Is that you have it's basically iron core with two separate irons, just like impedance matching that we learned from passive filter section. Then you have let's say the number of turns in the primary and secondary, the voltage ratio is the same. So it's actually, the more turns you have in the side, the more voltage you will have in that side. So in other words, if you have the primary to secondary ratio of 1 to 100, and then the turn ratio of 1 to 100, then the voltage in the secondary, if it is 1 to 100, then the secondary voltage will be boosted up by 100 times. Then what do you think we will be losing? If you increase the voltage, what do you lose? Current. That's the key thing, right? We increase the voltage to decrease the current proportionally so that the power loss will be less. If you are saying that you have the same energy, you increase the voltage and everything remains the same, of course that's lie, right? So you are actually compensating that with at the cost of lower current. And lower current is required here because for the power transmission, the loss is strictly related to square of the current that is flown. And that's how it works. So let's take a look at how this is going to be transferred. This is the concept of the transformer. So you have the iron core with the magnetic flux, the primary side with these coils going, the magnetic flux is transferred, is going to be generated, and then that flux is going to rotate around this transformer core, which that flux can be captured from the secondary side, and that will generate the current proportionally. You have lesser number of turns, that means the current will be higher, the voltage will be less. That's going to be proportional. Now, in that context, the the flux amount can be denoted as, this is induced across the induction law, d phi over dt. The number of times, over time, how much flux is generated multiplied by number of turns, that translates to the the voltage across the secondary. So for example, this magnetic flux itself remains the same, so it has to be the same across the primary and the secondary side, and proportionally the number of turns will be relevant to the voltage being generated there. So this is why this remains a constant. That means the ratio of the secondary to primary turn ratio is the same as the voltage ratio of secondary to primary, because this doesn't change. Okay, if you have more number of turns, more voltage you'll get. Now, this is the ideal power equation. In other words, power incoming is the same as power outgoing. So it means that the current multiplied voltage should be the same. If you have a higher voltage, proportionally you have a lower current with the same amount of power. So this is why the number of turns in the secondary to primary is the same as the voltage ratio, and it's inversely proportional in current. Because, as I said, the power is the same, then the voltage multiplied by power has to remain the same. So the higher the voltage you get, the lower the current you will get, right? That's the key. And the same thing can be happening in your AC adapters. So to step up, you have the secondary larger number of flux. If you want to step down, you have less number of flux. So your chargers, like laptop chargers or tablet chargers, you plug in 230 volt, that will be stepped down to 20 volt, typically around 20 volt, and that's where the charger is going to be charged at. Sometimes the smaller appliances with the smaller current in USB, you use USB-A, like not USB 3.0, then it uses 5 volt, so you can step down further to 5 volt. So this is what the adapter happens. Inside the adapter, first of all, you are going to do the filter, filter that filters out the unwanted noise signal to get the pure sine wave. Then the transformer will be converting 230 volt in Singapore down to the voltage you want to use. That's the second stage you'll be doing. And then remember, this is an AC signal and your laptop uses DC. So you have to convert the AC to DC. That's what the rectifier does. So you have a dual phase, you have an alternating current, which will be transformed to unidirectional current, which is like this. The rectifier by right is always coupled up with the storage capacitance to smooth out this ripple. And that's what the rippling after the reservoir filter or the storage capacitance, it will be in a unidirection with some ripples on it. The larger the reservoir, the less ripple you will get, but still you cannot get away the ripple completely. So then you need to have a voltage regulator to change that the alternating ripple into a constant DC. Basically, today what we'll be learning is how to do the voltage regulation as well as line regulation. We'll be talking about the variance of the under load condition or the ripple in the input, how you make it a constant DC voltage. Right? Rectifier, reservoir, as well as the voltage regulator. So let's take a look at voltage regulator. So you have the transformer that changes the AC into step down. You can see the number of secondary is less in turns. That implies the voltage will be less in the secondary. And after the rectifier, this is called full bridge rectifier. your voltage will be unidirectional with the capacitance, but the output level will be fluctuating like this with some DC voltage. Right? This cannot be used directly in your electronics because especially your CPUs and these electrical circuits are, electronics circuits are very prone to ripple and either fail over, it'll get a lot of stress. So that's why this ripple has to be regulated into a clean DC as much as possible. So there are two types of regulators. First is the shunt regulator, where the control element is placed in parallel with the load, the shunt part of the load. We'll come back to that. And the second is more commonly used, the series regulator. So series regulator is where the control element is placed in series with the load. The voltage drop across that subtracts the input voltage to get the regulated output voltage. But that is more commonly used version. Okay, so let's take a look at the series and shunt regulators. But before we go to that, one core circuit or device that is used in the regulator is called Zener diode. So the regular, typical diode has a characteristic it flows unidirection this way. And if you have the VD that goes beyond around 0.7 volt, it abruptly flows the current. That's a forward bias. In a reverse bias, the nominal diode blocks the unit and then it goes to breakdown. Avalanche breakdown happens at typically minus, let's say, depending on your diode, it differs. Sometimes minus 7 volts, sometimes minus 12, minus 20 volts. But you don't have a controlled voltage there. Whereas the Zener diode, in other words, the regular diode, you don't use this intention, and you don't typically even go close to this breakdown voltage because that's unregulated and uncontrolled voltage for regular diode. But there's a Zener diode, which you control the dopant, and you have a predetermined value whether it will give away in the reverse bias. And that's a control voltage. So if you buy a Zener diode of VZ of minus 10 volt, it'll always flow reverse current at minus 10 volt. Up until 10 volt, there's insignificant amount of current flowing, but once you hit the Zener diode voltage, then it will flow in the reverse bias as well. So that's the difference between the regular diode versus Zener diode, is that Zener diode is meant to flow reverse current under certain level of reverse bias. Now, why is it important? By the way, Zener diode compared to the regular diode is denoted by this sign. You can see there's a small slanted symbol over there. And this can be modeled as reverse bias Zener diode breakdown voltage plus the series resistance at that moment when it flows the reverse current. Right? That's how you're going to reverse show it. And that's a resistor RZ, which plays a role in the voltage regulation. We'll be coming that in the coming slide. Okay, looks like now the AC is on, but it takes time to get it cooler. Okay, so a simplest possible shunt regulator looks like this. So you have a Zener diode with a load, and you can see that the load is in parallel with the regulator. That's why it's called a shunt regulator. So there's a source resistance and then Zener diode. And as I said, Zener diode can be modeled as a reverse bias current, voltage of VZ in series with the series resistance RZ. That is the Zener diode model for circuit. And for this, we do some analysis. What will be the voltage at the output so we call it V load voltage under these conditions? You might be puzzled, but by simply having the reverse bias Zener diode like this, it achieves the regulation, meaning that if you have a fluctuation like this, the load will be constant. That sounds like a magic. How does that happen? Right? So that's what we're going to do the analysis. So how we do it is as follows. KCL, current flowing in is the same as current flowing out. So then let's say this is the voltage load, which is VL. So VL, the RS with IS will be IS is equals to the input voltage minus the load voltage over RS. That will be the IS, which is equivalent to load voltage, which is IL, which is VL divided by RL. That's the load current, RL, and then IZ over here. And IZ, as you can see, is actually VL minus the VG, that is the voltage over here, over RZ. So then IZ plus IL is equals to IS. And then we can do some analysis. I repeat, this current, which is the input voltage minus VL over RS, is equals to VL over RL, which is the IL. And then VL minus the VG will be the voltage over here, which will be divided by the RZ. So those combined is the same. So this is what I'm saying. And IZ is the load minus VG over RZ. This is IZ. And if you plug it in, the load voltage is equivalent to input voltage multiplied by the voltage division over here with the VG minus IL, RS in parallel with RZ. This is what we're going to get. And if the RS is much, much greater than the RZ, typically that is the case. The reverse series resistance of RZ is lower than the RS. Then you can see that the RZ can be almost ignored. This can be ignored. It's equivalent to almost RBZ. And RS in parallel with RZ, because RZ is very smaller, RS can be ignored. Then roughly speaking, load voltage will be the same as the Zener diode voltage. So if the Zener diode voltage was, let's say, minus 10 volt, and you go the reverse bias like this, then even with the fluctuation in the input, your output will be almost always 10 volt and stays at 10 volt. Right? So then where does the ripple go? The ripple is going to be flowing as a reverse current in the Zener diode. So in other words, Zener diode will be absorbing those ripples. That's what the shunt regulator does. Okay? The way I derive this equation is the IZ and IS will be inserted into this KCL, and then that's a resulting equation you're getting from here. Okay? Now, you need to also take a look at it, carefully observing the load voltage is function of the input voltage and the Zener diode and the load current, as you can see. And although if the RS is greater than RZ, you can approximate load voltage to that of the Zener diode reverse diode, you also want to see how well this regulates in terms of each variable, such as the input voltage fluctuation, Zener diode itself, as well as the load current. So in order to look at it, what you can do is that you can take a partial derivative. So for example, how well the delta load fluctuation goes with respect to the fluctuation in the input. That's what you call it the input regulation factor. Okay, input regulation means you're changing your load, input is changing like this, how well you stabilize the output. That's the input regulation factor. And that means you have to take the partial derivative of the input change. That means if you take the partial derivative of delta VI, these two are constant, so they will go away. Then the rest is SV. That's the input regulation factor. Similarly, if you have change in the output resistance, meaning that if you have a change in the load, you want to also take a look at it, how much it will be affecting the regulation factor. In other words, in the previous diagram, if you have changing in the load resistance, this happens always. Your load resistance may not be a stable value, and it may change, then it will fluctuate the IL. So under that IL fluctuation, how well you are maintaining the output level, that is with respect to the delta IL. So you take the partial derivative of the IL, these two are constants, they go away, then R naught is the output resistance, which actually denotes how well you're regulating the output with the changing in the load resistance. And the last thing is the delta T. So over temperature, it will also fluctuate. And ideally, even with the change in the temperature, you want to have a constant output, but it may not be always that. So this is why a good quality regulator has delta V as small as possible. With respect to the input change, with respect to the output load change, as well as the input, the temperature change, you want to have a constant output. So let's find, so for example, find the expressions for the input regulation as well as the load, as well as temperature regulation for the Zener diode shunt regulator. Then this is the equation. As I said, for the input regulation, you will take the delta VI so that everything else will be constant except the VI related. For the VI, if you take the derivative, VI will disappear. The only remaining is RZ over RS plus RZ. That's over here. That's what you're getting for with respect to the input change. Same goes with the change in the load resistance value, IL. The only thing left over is the RS in parallel with RZ in that case. And if you change over temperature, then RS divided by RS plus RZ. This is the change in temperature which affects the output level and how well the regulation will be done. And remember, this is all for shunt regulators, just like this configuration. Okay? But there are forms, regulator, that are required to produce a DC voltage which is independent of the line voltage fluctuation. And in other words, the voltage there are two metrics or figure of merit a voltage regulator should have. Is that one, if you have a fluctuation in the input, you want to maintain the output as stable as possible. This is one thing. And the second thing is your load resistance changes, varies very lot. And then you want to maintain the output voltage to a constant level. These are two things that has to be kept well. And under the load changing condition, load is changing as a high load resistance to the lower resistance, and you maintain the output level. That's called the voltage regulation. And under the change in the input fluctuation, you want to maintain the output to a constant level. That's called the line regulation. So line regulation is determined by change in the input voltage, which is dividing the change in the output voltage. So if the regulator is perfectly working, it doesn't matter how much you're fluctuating, the output will be DC. That means delta VL will be 0. So line regulation, if it is well achieved, should be 0. And voltage regulation is defined as the open circuit and then closed loop circuit. So full load means that you have a full load of current flowing. No load means that the load has no impedance. I mean, it's no load condition, and then open circuit. Full load is when the current is flowing the maximum. You have the voltage difference between these two, which will be divided by the full load condition. That's the voltage regulation. So both full load and the voltage regulation and line regulation are important metrics in a voltage regulator. So we'll have an example about the line regulation and voltage regulation. So we'll take a look at that once we hit that example. But shunt regulator discussed above is good, but it provides the load current obtainable from output is limited to several tens of milliamps, whereas your appliances these days typically require tens of amps, especially even your fast quick charger, your smartphone. Even smartphones these days require several amps or even further, like 10 amps, even higher. And that cannot be achieved by the shunt regulator. So this is why we use a power transistor here and then use the series regulator. So this now the regulator is the load is in series connection. This is why we call it series regulators. And you can actually flow a lot of current to the load with this configuration. So this is how the series regulator works. You will have the transistor with the Zener diode, which has the source resistors connected, and the load will be connected to the emitter of this T1. Right? This is no exception with an NPN, so the MOSFET version. Although the MOSFET version, we typically use PFET for this configuration, so I'll come back to that. But BJT, we typically use NPN transistor for this. Okay, so in this case, let's take a look at it. You will see that the base voltage minus the VBE will be the output load voltage. In other words, VDZ minus VBE of T minus 1, T1 will be the load voltage. The VDZ is the reverse bias voltage of the Zener diode. You can see that. This is the VDZ, and VDZ minus the VBE will be the load, as you can see from the schematic. Right? This we learned from the transistor amplifier. So in this case, we'll be noting that it consists of two parts. a power transistor T1, and a Zener diode in the series regulator. And this is the key. The load voltage over here will be the VDZ minus the VBE of the transistor in series. And this is the regulation factor. So this will be constant. Why? Because VBE is almost always 0.6 volt for the power transistor, 0.7 for normal BJT. Although it has slight fluctuation over temperature and also the load current, it has slight change, but nevertheless it's almost constant at 0.6 for power BJTs. And VDZ is also almost constant. That's how the Zener diode is made. The reverse bias voltage, breakdown voltage is almost controlled. So hence the load voltage will be always, once you determine what the VDZ will be, and the VB is almost constant, so therefore the load voltage will be also almost determined. That's in theory, but in reality, VDZ fluctuates with respect to the temperature change. And also the VBE also changes with respect to the temperature as well as the load current. So it's not perfectly, let's say, DC, but there's some fluctuation. But nevertheless, it achieves good enough regulation factors. Now, I said the VBE actually changes with respect to the temperature as well as the load current, and it is because the load current, i.e. the emitter current, is actually proportional to the exponential of the VBE over VT, where the VT is 26 millivolt. And VT, that itself changes slightly with the temperature variation. So if that changes, you can see that the exponential of that will consequently change as well. So this means the VBE is actually not a constant by the VBE. So VBE is also a slight change there. And when the input voltage changes with the fixed RS, Zener diode will have to handle an extra current. So if the input change is excessively large, Zener diode has to absorb that current. And if the amount of current flowing through this load is enormous, Zener diode may not be able to sustain such high current. And why is this not a problem in the shunt diode is because shunt diode typically you only have load current of several tens of milliamp, whereas here the load current may be in terms of tens of amps. So the extra current that you have observed through the Zener diode may be really, really large. And that may potentially damage the Zener diode. So to prevent this, what we do is that we have a voltage regulator with the negative feedback. So this is how it works. So you have the voltage ladder of R1 and R2. So you can see that the load voltage will be divided by R1 and R2. That is KVL. KVL is the voltage division ratio of R1 and R2. That is fed by the error amplifier. And if the error amplifier senses the voltage at the load is too large, if the load voltage goes up, proportionally KVL also goes up. You sense that with the error, you compare that with the reference, and if the KVL increases, you start decreasing the base current. If the base current decreases, so does the load current. If the load current decreases, the voltage drops. So you started off from the voltage level increasing in the VL, you sense the error amplifier, you give a negative feedback to the base current, which lowers the load voltage. So you can see this is a negative feedback fashion. That's how the line regulation, the regulation happens in the voltage regulator with the negative feedback. So error amplifier is the key which controls the base current. And notice the load current is beta times the base current. Beta times the base current is the load current. So if you decrease the base current, so does the load current. Okay, that's the key. So in this case, first of all, the load voltage, as you can see, is the input voltage minus the VCE, VI, minus the voltage across the collector to emitter. That will be the output voltage. And to ensure the pass transistors are not saturated, do remember, we learned this last week. In order for this transistor to remain in forward active, this VE and VB, VBE has to be 0.7 for the nominal BJT. For power BJT, around 0.6. Base has to be higher. And this base has to be higher than VC to be in full linear region without saturation. And the bare minimum you have to guarantee was at least 0.2 volt across the collector to emitter. But I said that's when the transistor gets into saturation. And even before you reach to this value, if the collector value goes too low, then distortion heavily happens. So if the good designer, if I'm a good designer, probably I'll multiply this by 10 and give no less than 2 volt difference between collector and emitter. If that's the case, you can see that the collector will be much greater than base. Base will be greater than emitter, and this will be in fully active mode. So this is why I would probably give the input to the load voltage difference to be at least 2 volt. Meaning that the load voltage has to be at least 2 volt lower than the input voltage so that it remains in high, let's say, very stable without any distortion. And in this case also, if you look at the previous slide, we call this sampling network because it samples the current, samples the voltage in the output and gives the input to the error amplifier. And do you want to have high current through this network or low current through this network? As low as possible, because the purpose of this current, this sampling network, is just to sample the voltage. You don't want to consume too much current through this network. So this is why we typically design a way that the current through the sampling network is much, much less than that of the load. When I say much, much less than 1,000th. That's how we typically design. And how do you, next question you have is, how do you actually make this error amplifier, right? And this is why we learned OPM first. It's because we typically use the OPM for an error amplifier. So the way it works is as follows. It looks very puzzling, but don't panic. This is how it works. If you have voltage increasing, so does the KVL. If the KVL increases, it is coupled to the negative port of the OPM. So then if KVL goes up, so does the negative port. If the negative port goes up with the same voltage in the VR in the plus port, the output will be decreasing because the negative feedback has increased. If the VO decreases, the voltage at the base decrease, then so does the voltage at the emitter. So you started off with the increasing voltage. By the time it comes back with negative feedback, it lowers the voltage at the load. That's what the negative feedback is about. That's how this behaves. All right? So let's do the analysis a little bit more in detail. First of all, the VR over here, VR is the K multiplied by the load, where the K is the voltage ladder of R1 and R2. Right? So then you can see that the K is the voltage divider, and then the load voltage will be VR divided by K. Okay? This is the first line of analysis. Then you can see that the Q1 provides the current gain to absorb the difference in the voltage between input and the output. And then you will see that the error amplifier will absorb the difference, and then you give the constant voltage there. And as I said, you want to maintain at least 2 volt difference between the collector and emitter so that Q1 doesn't distort any signal, right? That's a good design that you want to have. Any questions up to this point? Probably it's a bit difficult to understand, but if you go to the example, then it'll be easier to understand. So I'll come back to the example in 3 slides. So, but before we go to that example, let's do the power estimation, power dissipation estimation. Voltage across the pass transistor is the Q1, is the VCE, which is the VC minus VE, right? That's the input. VC is the input, VE is the load voltage, and power dissipation in pass transistor will be the voltage difference, which is VE minus V load, multiplied by the current passing through it, all right? And assuming there's current through R1 and R2 is negligible, and that is intentionally what we do for the sample network to draw meaningless amount of current, right? And at this point, V input minus V load has to be greater than 2 volt to avoid saturation. I already mentioned. So in this case, if you do the observation, input minus VL should be greater than or equals to 2 volt. but the efficiency is quite low due to the fact that you have 2-volt difference in the input to the load. The eta is the power delivered to load divided by power supply to input, which you learned last week, multiplied by 100%. The pass transistor conducts a large load current continuously, so the power dissipation in pass transistor is rather large. That's the payment. That's the price you are paying for good line regulation. Okay, but one thing to remember is you don't want a situation where the Q1 is conducting too much current. And that may damage not only the Q1 but also the error amplifiers and the remaining circuitry. So what you can do is, in that case, if the base current is too large, you want to probably shunt it away so that Q1 remains within the thermal. We learned about thermal breakdown last week. Remains that power dissipation through Q1 is within the the allowed range. And how can you do that? Is by inserting a normal. This is a power transistor. This is a normal BJT, like this. And you have a very small series resistance. The way it works is that once you have, once you have some amount of current flowing, and then let's say this one turns on at 0.7 volt, you design the resistance value to, let's say your allowed amount of current flowed is 10 amps. In this case, this resistance voltage drop at 10 amp will be 0.7 volt. This is how you design it. It means that the series resistance will be 0.07 ohms, very, very low. But once 10 ohm is flowing through the 0.07 ohm, then there will be a voltage drop of 0.7. And if you look at Q2, that's the VBE. That turns on the Q2. If Q2 is turned on, you can see that the error amplifier's output, instead of going all of them going to the base of the pass transistor, some of them will be shunting away through Q2, directly to the load. So that instead of increasing the base current, some of them will be shunted away directly to the load, so that you cannot increase the base current of pass transistor above certain level. Because above certain level, the pass transistor will trigger the Q2 operation, and when the Q2 is on, then no more base current is flowing through the pass transistor, but rather some of them will be flowing through the load directly. So then there's a certain level how much current will be flowing, and that's why it's called the current limiting or overload current limiting circuit. And this is very, very important to avoid damage in Q1. Okay, so to summarize up to this point, these two look the same in the schematic, but actually this is a power transistor that potentially can flow tens of amps, whereas this Q2 only flows several milliamp of current, so that it can actually shunt away excessive base current to the power BJT. Any questions up to here? Let's take a careful analysis here. So the way you design it is to turn on. You only turn on this Q2. In other words, voltage drop of 0.7 volt happens when you hit the target load current, limiting current. So it means R multiplied by the Lmax, ILmax, should be less than that or equals to that of the VBE of the pass transistor. Current limiting transistor. So that load current flowing is always less than the ILmax, because once you hit the ILmax, Q2 will be shunting away the current. This is what the current limiting circuit does. Okay, so let's take a look at how this behaves. When the load current increases to a certain extent, the voltage regulator goes to, the regulator voltage output is constant, but above certain level in the load current, abruptly it cuts off the pass transistor so that no more regulation happens. This is to avoid protection. This is to protect the power BJT to fail. Right? This is how it behaves. And you look at the example, because without the example, it will be very puzzling. Okay, so design a voltage regulator to meet the following specification. Maximum load current will be 2 amps. That's a lot of current. Regulated DC output voltage is 20 volt. This is just like your laptop adapters. Regulated DC input voltage fluctuation is from 25 volt to 30 volt. Output short circuit protection is required. This is what it means. You need to have a protection circuitry. The following devices are available. Operation amplifier, maximum output current will be 20 milliamp. Zener diode, the VZ has 6.8 volt. Breakdown current is 1 milliamp. And the transistor BVE will be 0.6 volt. So this implies this is a power BJT. And you might be thinking, how can Zener diode of 6.8 volt generate the load voltage of 20 volt? So you can see that the shunt regulator cannot be used because shunt regulator output will be roughly the same as the VZ. So this implies we have to use the series regulator. Now, how do we design this? Well, there's one hint. Specify the power rating of all the components, and on top of that should draw a current of less than 1,000th. The sample network should draw less than 1,000th of the load current. Since the load current is 2 amps, this implies the sampling network should draw less than 2 milliamp. Right? So where should we start from? We start from the schematic. So there are several things to design. First of all, the sample network, which should draw less than 2 milliamp because 1,000th of the load current, which is 2 amp. And at 2 amp, this Q2 should turn on. So at 2 amp, 0.6 volt voltage difference should be given in VBE. And the maximum output current of VB, the OP amp is 20 milliamp or less. And there's an unregulated voltage of 25 to 30 volt. Regulated voltage to be 20 volt. And the Zener diode has 6.8 volt difference. Okay, those are the specifications. So where do we start from? We start from the following. We first see that load voltage is 20 volt. We also take a look at our R3 value. We determine that. That can be derived from 25 and 30 volt differences with respect to the 6.8 volt. And then we design the sample network R1 to R2 network ratio. And then lastly, you design the power transistors. So first of all, what we need to do is follows. The load current, which is the load voltage divided by RL, which is 2 amps. And this means at 20 volt, you have maximum current of 2 amps. What does that mean? Your load resistance should be at least 10 ohm. Why? Because if your load resistance is, for example, 0 ohm, if it means, okay, 0 ohm is not realistic. Let's say 1 ohm, and the maximum load current was 2 amps. Then 2 amp flowing through 1 ohm, the voltage will be 2 volts. That's not equivalent to 20 volts. Since there's a finite amount of current that you can flow, there's also finite resistance that has to exist to maintain 20 volt. And how do you calculate that is to divide the target load voltage by the minimum and the maximum current that we allow to flow. So 20 divided by 2 means 10 ohm. This implies unless there's at least 10 ohm resistance, you cannot maintain 20 volt. If the load voltage goes less than 20 volt, then you will be failing to regulate at 20 volt, maintain 20 volt at the output. That's where the output protection circuit should be there because while you're working, because of various reasons such as the wire being the insulator failure, or sometimes you accidentally connect the load output directly to ground, short circuit to ground. In those cases, you need to make sure that the regulator cuts off itself so you don't overheat. So that's why the protection circuit is needed. But with this 10 ohm, you can see that the load resistance, maximum current flowing is 2 amps square multiplied by 10 ohm is rated 40 watts. I already told you how large 40 watt will be, right? Light bulb typically consumes 60 watt when it's operating, you cannot touch it. But small resistor with 40 watts, oh my God, that's crazily high rating. So this is why in the lab, which I will post in tomorrow, lab sheet, you'll see that if the load resistance is, you see anything like 2-3 watts, then you should be using power rating power registers, which is physically bigger than the nominal, small, this type of resistor you see with stripes like this This is typically 1/4 watt maximum, 250 milliwatt. So if you put this load resistance with this type of nominal 1/4 watt rating resistor, it'll blow up, literally blow up. So be careful with that. So this is why checking today's lecture and then do the power rating for your lab calculation is also important. For the Zener diode, input minimum should be 25 volt, and Zener diode has 6.8 volt, and the IZ, current through the Zener diode, was given as 1 milliamp, so it should be 18.2 kilowatt for the R3. What is this meaning? Right? The reverse current through the Zener diode should be 1 milliamp minimum. So at that minimum value, the voltage should be minimum. And minimum is 25 volt. So the 25 minus 6.8 over R3 should be flowing 1 milliamp. That's why you choose 25 volt and then you subtract it by 6.8 divided by R3, which is 1 milliamp. Where does that 1 milliamp come from? I repeat, coming from here. Breakdown current of 1 milliamp. Okay, why you don't choose 30 volt? Because if you choose 30 volt for designing that, it means at 30 volt you'll be flowing 1 milliamp. So if you're giving 25 volt, it doesn't do the reverse current. It doesn't break down. Then it's not going to work as a regulator. This is why minimum of voltage, you want to have 1 milliamp flowing minimum. So therefore, you need to have 25 volt for these calculation purposes. And that actually gives us 18.2 kilo ohm should be attached to the R3. At that point, the maximum possible current through the Zener diode is, we calculated 18.2 based on minimum, which is 25 volt, and maximum we put over 30 volt. So with the same calculation, 30 minus 6.8 over 18.2 means 1.27 milliamp. So the rating, power rating for the Zener diode is this one square multiplied by the Zener diode resistance, or the Zener diode voltage of 6.8 multiplied by 1.27, which is 8.67 milliwatt. So you can see that the Zener diode doesn't have to be crazily high voltage. It only consumes very little amount of current. Are you getting the message? The load resistor has to sustain such a large power wattage. You may even need some fan with the power with the heat sink, whereas the Zener diode, you don't need that. Now let's go to the power rating of R3. So the R3 itself is the sampling for the Zener diode here, maximum 1.27 milliwatt, milliamp, multiplied by the 18.2 kilo ohms, it consumes around 30 milliwatt, and that's well below the 1/4 of watt, so nominal resistance can be used. Dip type nominal resistance can be used for this one. Now, then what is the feedback voltage? The feedback voltage is 6.8. How do I know? This is 6.8 volts. Plus and minus port has the same voltage, no potential difference, so it should be 6.8. Your target VF should be 6.8 consequently. So these two voltage divided results should be giving VF of 6.8 out of 20 volt output. So you have one equation with two variables, R1 and R2, two variables multiplied by 20 yields 6.8. Hence, one rate equation is R1 is equals to 1.94, 1 multiplied by R2. Please don't be obsessed about numbers here. There are some tolerances. But again, if you just have this one equation, there are millions of combinations you can choose R1 and R2 from. But there's another limiting, which is the sampling network should not be drawing more than 1,000, meaning that I should be 2 milliamp or less. So therefore, R1 plus R2, which is 20 volt divided by R1 plus R2 is 2 milliamp. Therefore, R1 and R2 combined should be 10 kilo ohm. Then you have two equations with two variables. Then you can pinpoint R1 and R2 value, which yields 3.8 for R2, 1.9 multiplied by 3.4, which is 6.6 for R1. And for this sampling network, if you do the power rating, they are each less than 30 milliamp, so 30 milliamp. So again, a milliwatt. you can just use the nominal quarter of watt rating registers. Any question up to this point? That's also possible, but that'll be an overkill because the size of the, probably, I typically bring this 2-watt resistor, which is already pinky size, but it's too bulky for small microelectronics. So you just want to use right size resistors for right rating. But of course, theoretically, if you use the old, let's say 2-watt or even 10-watt compatible resistors, you can sustain no problem. Mega ohm. Oh, you mean for the sampling network? You can also use sampling network with a mega ohm even higher, but now, what is the downside of using too large resistors? One is the size, noise. Because the thermal noise will be coupling. I enjoy the response from this group. So if you use the too high resistance here, the thermal noise from these resistors will be coupling to the load. And if your load is really caring about the noise, you don't want to use too large. You just want to use right amount of resistance. But excellent point. Okay. For the transistor, we also need to look at the power rating of the transistors because we need to decide whether the nominal black plastic covered BJT can be used or aluminum casing power BJT be used. If it is a MOSFET, should I use the small MOSFET or power MOSFET? You have to determine it by checking the power rating. For Q1, the maximum emitter current is 2 amp because 2 amp plus 2 milliamp is 2 amp. This is less than 0.1% difference, so you should get it as 200 semi. Maximum available base current is 100. Okay, if I use the base power BJT, the beta is not 100. It will be probably 2030, so the maximum base current will be even higher. But assuming this is a nominal BJT, the base current will be 20 milliamp. So beta will be 100. Maximum power dissipation in Q1 occurs when the output load is short-circuited, meaning that your output is directly connected to ground. Then your load current will be maximum, consequently. So in that case, of course, in the real situation, because of the protection circuit, this never happens. But in load, if you short the output to ground, that means the load voltage is 0. So Imax, input max is 25 to 30 volts, so it's 30. Minimum load in short circuit is 0. So the voltage difference between collector and emitter will be 30 volt maximum, theoretically. And you're flowing 2 amps. That means, oh my God, 60 watt. So the light bulb of 20 square centimeters, you cannot touch it. And now you have a power BJT of around pinky or less, consuming 60 watt. Definitely you need a heat sink. You may even need a fan right, to forcefully induce some air into that fin. So anyways, in that case, what is the cut-in voltage in the protection circuit? Okay, when 2 amp or more is flowing, you want to make sure 0.6 volt is triggering Q2. So this implies you have to divide 0.6 by 2 amps, which implies the series resistance for protection circuit should be 0.3 ohms. That's a low resistance. You do have low resistance. However, should that low resistance imply that you can use quarter watt rating nominal dip type resistance? Let's check that. Power rating should be the current square, which is 2 square multiplied by 0.3, it's 1.2 watt. And if you use this nominal quarter watt rating resistors, it'll pop out, it'll blow up. So you can see that although the schematic seems same resistance, just to summarize, in the schematic they look all the same. But as a consequence, you can see that this one and these two can be nominal quarter watt rating resistors. This one should be power rating power ratings, although it's only 0.3 ohms, you should use the bulky resistors, as well as the load resistor should be really, really sustaining high current. Q1 should be able to absorb 60 watts maximum. You definitely need a heat sink, probably with the fan as well. Q2 can be nominal BJT, right? And then the Zener diode only consumes less than 10 milliwatt and 20 milliwatt or less, so you can just use the nominal Zener diode. Yes, you have a question?
Oh, well, no, but I guess I did.
Okay. Yeah.
How do we power the op-amp?
Yeah, this is excellent question. If you just use as is, it doesn't operate as intended. You always need to have an OPM power. It should be given separately. This is what I'm saying. In the lab, the first thing you need to check is make sure, first of all, use the oscilloscope to check if the output is actually properly given. Don't believe the 20 volt from the power supply means your 20 volt is actually coming. You have to actually measure it with the oscilloscope. And don't forget to increase the limit in the current. Otherwise, the power supply may be outputting 20 volt with very little current. Then your OPM may be demanding more current, then it doesn't work. So that's the first thing you need to do. The answer is you need to couple up OPM with a separate supply.
So we need to have a separate power supply just to power it.
Just power the OPM, this is correct. So of course, in the integrated circuit version, you have to have your own circuit power supply to supply the OPM at the same time. Of course, the OPM is not going to be as accurately affected by the load voltage, so you can have a slight fluctuation in the OPM supply. But the regulator, you should have a chip regulator which provides the supply to the internal circuit as well. Yeah, excellent point. Yes?
So what actually controls the output, like load voltage?
In particular case, is combination of the Zener diode VG plus the OPM coupled up with the base current of Q1. The base current of Q1 is actually the dominating factor to control the negative feedback. But you can see that 0.6 is the offset you have. On top of that, you have the negative feedback from Q1. Does that answer your question? Yes.
So if I wanted to change the voltage and maybe drop it to 10,
Then you have, if you want to change the voltage to a level of 10 volt, yes, of course, you have to, because as you can see, everything has changed from the sampling network R1 and R2. So if you want to drop it, probably I want to control the R1 value so that the resulting RF is still 6.8 at lower load voltage, yes.
For the sampling voltage, it's 1 over 1,000 of
Or less of.
or less of. Is this general rule?
Yeah, so I would say this is a rule of thumb for, you don't have to follow this way, but I would say good balance between the resistance-induced noise versus the power consumption of the circuit. Yes, that's about the ballpark you want to do. Probably 1/2000 is also allowable. 1/5000 will be also okay. That will be about the ballpark you want to design. And same goes for the CMOS version.
So because you want to sample and create this negative feedback, you need to do a bit more current.
That is right, yeah. Now, if you understood this correctly, let me tweak this a little bit. If you want to use Q1 with a PNP transistor, how would you do that? That is correct. Do you see that? Can you see that if this is a PNP, you have a more higher voltage here, you want to decrease the base voltage, or base current, or increase the base current in PNP? In PNP, in order to flow more current, your base voltage should be lower. In other words, if you want to flow less current, your base voltage should be higher. So, more voltage, you want to flow more current, then it should be swapped. So the positive port and negative port, if it is a PNP transistor. Can you see that? And since this is a PNP, where should this protection circuit be inserted? It's an interesting discussion to go ahead. Like this, with plus and minus. Let's think about it. If you want to insert the protection circuit, this is the VBE, that VEB in more specific, you have to provide. When the VBE, when the current flows with more than what you want to make sure there's a flow of current that shunts to the load or to the base directly. Can you make a guess? This is where your small tweak of questions can induce some thinking, right? So here, overprotection for the NPN was over here replaced. So in case there's an excessive current, you were shunting that to ground. In PNP case, if the current is more excessive, you want to flow more current into the base, and that can be shunted directly to the base, so you should have an overprotection circuit over here. Can you see that? All right? And for MOSFET, okay, this is out of the scope of EE3444AC, but since we are doing, okay, never mind. I think this will be too much. I don't want to overload with some more information, but MOSFET are typically using PNP equivalent, which is PFET. And the reason is because PFET has, NMOS always has threshold drop, meaning that you cannot pass the same voltage from here to here in the full VDD. Whereas a PFET can pass the full VDD to the other side. And if you don't want any voltage drop more than what you want, you'd better use PNP transistor, PFET transistors. So that's, So that's why the MOSFET typically you'll see the PMOS instead of the NMOS in this pass transistor power BJT or power PMOS. Anyway, that's actually more than what I wanted to cover today for this topic, so let's move on. Okay, and let's take a look at the monolithic regulators, so like IC regulators. Industrial standard will be providing 5, 6, 8, 12, 15, 18, and 24 volts. And you might be puzzled, why do we need like such high voltage regulators? And still we use 3.3 and 5 volt. Now additionally we have 3.3, 2.5, and 3.3. But more commonly used in electronics like your tablets and PCs will be 3.3, 5, and up to 12 and 15 volts because your PCIe and also this I/O with the PCs, they still rely on 20 volt, even 12 volt signaling as well. So that's why you need to have these high voltage compliant I/Os. It must have a short circuit protection circuit because it happens. Your adapter may be accidentally shorted to ground, and you must make sure that it doesn't trigger the, circuit breaker in your house. You don't want this faulty adapter to trigger the circuit breaker in your house. Sometimes it does, so that's why you need to have a good protection circuit. And you also have a thermal shutdown as well as the output transistor safe operating area protection. And this is what we learned last week. You don't want to excessively consume power. Okay, this is a typical application of the IC regulators with, okay, let me ask you this question. What does CI and CO do in a layman's term? Okay, let me change my question. What type of filter is this, CI and CO? It's a low pass, you can see that now, right? Any fluctuation shunted ground, DC doesn't pass. This is a low pass filter. So it'll provide additional, I would say, regulation. And typically, 1 microfarad will be used for the tantalum capacitors, whereas the less than 1 microwatt will be ceramic. Ceramic is the typical yellowish capacitor you see. And even with the IC version, integrated circuit version, like a SND type, you see the yellow color, tantalum will be black color with the silver stripe on it. And I can tell you these capacitors are most prone device that fails in power supply. And I told you already my experience. This power supply in my server, to be more exact, that by the way, this power supply unit is not cheap. It itself is about, how much did I pay? Around $1,000 for that server grade power supply. And I can see literally with my naked eye, this electrolyte with white substance has leaked out and it has hardened across it. And next time when I have some time, I will desolder it and then try to fix it. But I don't want to try it on my server because I don't want to jeopardize anything. But that I can try. So it's still there in the lab. If you're interested in, you can come and take a look at it. Okay, now that's it for today's power supply section. So I will post the power supply tutorial contents and we will cover them next week. And we'll have around 10-minute break and we'll continue with 2 tutorials. One is the OP amp and the other one is the transistor amplifier. Sorry for torturing you, but yeah, but especially the transistor amplifier, while we're waiting, please try to solve it if you haven't, right?